Let's take a look at how to start some of these problems over here from this week's homework. Let's just go through them one by one. I'm not going to solve the whole thing, but I'll just get you started on them. So here's 45. We've got 100 kilogram block pulled at a constant speed of 5 meters per second by a applied force directed blah, blah, blah above the horizontal. What's the rate at which the force does work on the block? So we have two different formulas for work. We've got this is the rate at which the force does work on the block. So the rate of doing work is going to be power. So we're really dealing with power, which is work per time. And that can help us. Sometimes we have it as dW dt if it's varying. But the other formula we have for power is going to be F dot V, like that. And I think that that one is the best one for this one because we've got a force. Where's our force? Right here, and we've got a speed right here, and we don't even really need the mass right there. So the only thing we have to really deal with is the fact that this is a dot product. So if my force is this way and my velocity is this way, I need to know the angle between them. And so the power is just going to be the force times the velocity times the cosine of the angle between them. And then it turns out to be pretty easy. So you've got the velocity, you've got the force, where is it? Right here, and you've got the angle between them, and that's pretty easy to do. Okay, moving right along. 49. Fully loaded, slow-moving freight elevator cab has a total mass of 1,200 kilograms and required to travel upwards at a certain distance in a certain amount of time. And then we're talking about what's the average power required by the force of the motor. So this is going to be power is going to be work divided by time. And it's not instantaneous here. Well, it's going at probably at a constant speed, so it doesn't really matter whether it's instantaneous or not. So we're going to do two things here. We also have to find out that work is going to be the force times the distance right here. Let's just double check that the force and the distance are at least parallel to each other. And that makes sense right here because you've got, this is actually pretty interesting. Sorry, I skipped over here. There's a counterweight with this much force, this much mass, and there's this mass over here. So what average power is required for the force the motor exerts on the cab via the cable? Okay, so I just have to take that into consideration. So really what we have is here's the elevator, and we've got gravity going down like this, and we've got the force of the motor going up like this. We've also got, how can I draw this over here? There's the elevator going up and over, and then there's the counterweight over here. So there's some tension in this cable over here because things are going at a constant speed. The force of the counterweight over here, which I'll just maybe write as M2G, that's going to be the same as this tension in this cable over here since everything's moving at a constant speed. So that means there's a tension over here, and there's a tension over here as well. This tension is going to be the mass of the counterweight times G. So this force over here only has to overcome a little bit of the gravity over there. So let's figure out how much force we're really dealing with. This is going to be the mass of the elevator times G, and then this is the mass of the counterweight times G, and then this is what's going to be left over between those. So if we just use 10 for gravity, we've got 12,000 newtons on one side, and we've got 9,500 newtons on the other side, and just subtract those, and that's what it's going to be for this force. Once I know what the force is, I can put it in here, and then multiply it by the distance, which I know. And once I have multiplied my force times my distance, I'll get the work, that's in joules, and then divide that by the time, and then that'll get me my average power. Right, so just a little bit to think about, kind of thinking back in terms of net force and so forth. Okay, so this one, it's number 3, so it can't be that hard. It's just a lot of words in the problem. A large meteorite skips across the atmosphere, and it was pretty cool. It was really giant. We had the mass of the meteorite, and we had its speed. And had it entered the atmosphere vertically, it would have hit the surface with the same speed. So calculate the loss of kinetic energy in joules would have been associated with the vertical impact. So we're really talking about the change in kinetic energy, which is going to be the K, I always want to write K final minus K initial. The final kinetic energy is going to be 0 because it's hitting the ground and stopping. So we're really just trying to figure out the initial kinetic energy right there. And the formula for kinetic energy is just 1/2 mv squared. So really this problem is just doing 1/2 mv squared. Once you get that, that'll be in joules. And it'll be a pretty big number. So let's make sure that you're changing this 15 kilometers per second into 15,000 meters per second. And you're just doing 1/2 mv squared for that. and making sure that the second parts are expressed as a multiple of 1 megaton of TNT and so forth. So then you're just doing some conversions on this, but it's going to be a huge number of joules. Okay, the next one, a father racing his son has half the kinetic energy of the son, who has half the mass of the father. The father speeds up by 1 meter per second and has the same kinetic energy as the son. What are the original speeds of the father and the son? So this is kind of a fun problem. I don't want to tell you too much how to do it, but what I'll say is just set up some variables right here. So I would say K father, and the father has half the kinetic energy of the son. Okay, now I've also got the K of the father is 1/2 m father v father squared, and maybe this is v father initial, and the kinetic energy of the sun is 1/2 the mass of the sun times the velocity of the sun squared. The father speeds up by 1 meter per second and has the same kinetic energy as the sun. So maybe this should be kinetic father initial, and then this is going to be kinetic energy the father final is going to equal, oh, I don't know why I have a 1/2 right here. Sorry about that, everyone. There's no need to have a 1/2 right there. I was thinking 1/2 mv squared. Oh, no, it is a half because it's in the problem. Sorry, yeah, okay, it's half. Yeah, half. So now the final kinetic energy of the father is equal to the kinetic energy of the sun. So you can work it all out. Oh, we also have the sun has half the mass of the father. So the mass of the sun is half the mass of the father. And it's just playing with some variables and moving them around, and you can figure it all out. Okay, let's see what else do we have. This is the Cannon nuts and bolts. Sorry, the graph's on the back here. So this is actually really common for AP to give you kind of a weird looking graph and figure out what's going on. Let's just take a look at the graph over here. We've got work as a function of distance, and hold on. It says Cannon nuts and bolts is being pushed by a broom along a floor, and by a constant horizontal force. So that's nice. It's a horizontal force, so we don't have to deal with any angles. And we have the work versus the position, and 6 is the vertical scale. What's the magnitude of the force? So what magnitude of the force? Well, if we just think about, we've got work and we've got distance, and there's a formula that we have that's work equals force times distance. And once again, we don't need to deal with the angle inside of here. So if I graph work on the vertical axis and distance on the horizontal axis, if I'm finding the slope over here, it's really work divided by distance, and that's going to be force. So they're really just asking for what's the slope. That's kind of the idea behind this. It's a kind of a tricky thing to do that the AP people often do as well. And then I think that you can figure out, once you have the magnitude of the force, figuring out what's happening with these two things, just remembering from a previous video that work is change in kinetic energy. So that's K final minus K initial. So on the problem over here, sorry to keep flipping back and forth, but when it says I had an initial kinetic energy of this, what's the final kinetic energy at the end of 2 meters? Then you know that the work done at 2 meters, this was 6 joules. So at 2 meters, it was 6 joules of work, and that's going to be the change in kinetic energy. So it's actually a pretty easy problem. You're just adding. Good. Hopefully that helps you all out. And I don't think these problems are too tricky. It's just kind of a new topic and a new unit, so it's hard to get a handle on what's going on.